Now let us locate the problem of a potential energy of a diatomic molecule and finding the equilibrium separation between the atoms where force experience remains equal to 0. The potential energy of a diatomic molecule is given by U equal to A upon R12 minus B upon R6, where R is the separation between the atoms that make up the molecule, and A and B are positive constants. The potential energy is due to the force that binds the atoms together. Find the equilibrium separation, that is the distance between the atoms at which force on each atom is 0. Also find the nature of force when distance between atoms is smaller than equilibrium distance. Also find the nature of force when distance between atoms is more than equilibrium separation. Let equilibrium separation is R0, since U equal to A upon R12 minus B upon R6. We know in a conservative force field F equal to minus du upon dr. After differentiating U with respect to R, we get F equal to minus 12A upon R13 minus 6B upon R7. Since at the equilibrium separation R0, F equal to 0, so substitute the value of F to be 0, we get R equal to R0 equal to 1.12 A upon B ki power 1 by 6. Now for finding the nature of force when separation, between atoms is smaller than equilibrium separation and more than equilibrium separation, we differentiate the equation of force with respect to distance R. So calculate dF upon dr, we calculate dF upon dr, we find dF upon dr as shown in the equation. Since dF upon dr is negative when R is less than R0, F is positive, so force is repulsive nature, and when R is more than R0, force is negative, so nature of force is attractive. Now let us look at one more illustration based on principle of conservation of mechanism as shown in figure. A body of mass capital M as shown in figure with a small disk of mass small m placed on it rests on a smooth horizontal plane. If the disk is set in motion in horizontal direction with velocity v, then to what height relative to initial level will the disk rise after breaking of the body of mass capital M? The friction is assumed to be absent. Applying principle of conservation of linear momentum, we get small m into small v equal to small m plus capital M into v1, where small v is the velocity given to disk and v1 is the combined velocity of disk plus body. So v1 equal to mv upon m plus m. Let the disk rises to a height h Apply principle of conservation of mechanism. Let disk rises to height h. Apply principle of conservation of mechanical energy. We get half mv square equal to mgh plus half m plus m v1 square. That gives us h equal to mv square upon 2 m plus m into g. We can solve the same problem from center of mass frame. As we know, in center of mass frame, half mu v relative square equal to change in potential energy. So half m v relative square equal to mgh. Half mu v relative square equal to mgh, where mu is the reduced mass of the system. Mu equal to mm upon m plus m. We can write half mm upon m plus m v square equal to mgh. That gives us h equal to mv square upon 2 m plus m g.